Okay, this is section 15.1, the concept of equilibrium, a little introduction into the idea of what we call chemical equilibrium. So up until now, we've looked primarily at reactions which only go in one direction. So for example, if you take hydrogen and you combine that with oxygen to form water, the rate of the reaction is equal to K times concentration of H2 to the X times concentration of O2 to the Y, right? And experimentally, we would determine what X, Y, and K are. But in this process, we ignore the possibility that this reaction could occur, that two waters could be converted into two hydrogens and O2. Essentially what we would say is that the rate of this reaction is so small, it's approximately equal to 0, that we can ignore that process. The reverse reaction essentially doesn't occur. But now what we're going to do is we're going to look at reactions where that's not the case. And this is the concept of what we call equilibrium. So some reactions are said to be reversible, meaning that the reaction could go in either direction and actually goes in both directions simultaneously. The idea, an example of this would be the reaction where N2O4, dinitrogen tetraoxide, reacts in a decomposition process to form two molecules of NO2, nitrogen dioxide. Okay? If you were to look at that reaction and study it, you would find that the rate is equal to K times the concentration of N2O4 to some power, right? But it turns out that the reverse reaction is also possible. If we fill the container with NO2, we would find that the NO2 reacts with itself to form N2O4. And the reaction, this reaction, would also have a rate constant and an NO2 concentration. I'll call this Y, raised to the Y power. That reaction would also occur. So what we're claiming here is that both reactions can occur. If we put N2O4 in the container, it will form NO2. Or if we put NO2 in the container, it will form N2O4. That tells us that two opposite processes are occurring simultaneously. So we can write that in the following way. N2O4 is in equilibrium with NO2. Okay, we're going to write it that way. And if it's in equilibrium, at equilibrium, what we would say is the rate of the forward reaction, we'll call this the forward reaction. It's kind of arbitrary which one we call forward. We'll call the other one reverse. It's arbitrary which one is we call, but we'll do it that way. So the rate of the forward reaction is equal to the rate of the reverse reaction. Okay? And so if that's the case, then you could say K, F for forward, times the concentration of N2O4 to the X is going to be equal to Kr for reverse times concentration of NO2 to the Y. Now, suppose I went on and said, hey, it turns out experimentally we find that X is equal to 1 and Y is equal to 2. We just figured that out experimentally. It turns out that's true. Then what we could do is we could substitute those values of X and Y in, and we would have Kf times concentration of N2O4 to the first power equals Kr times concentration of NO2 to, I'm sorry, meant to make that a 2. We're substituting that in as a 2. Okay? We could do that as well. And what we'll do is we'll look at it a little bit later in the next section, the significance of that equation right there. But really what we're saying here is that the rate of the forward reaction is equal to the rate of the reverse reaction. Now let me show you a depiction of this, just so that we can picture it in our head, what we're talking about happening. The idea here is the following. Imagine we say A is going to get converted into B. I'm just going to use A and B just to make things simple. And so now I have this container. And initially I put in a bunch of A's. I'm only putting in the reactant. Over time, what you would find is the amount of A's would decrease, right? So now you'd have some A's in there. Let's count them up. 3, 5, 8, 9, 10, 11, 12. There's 13 in there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll just stop at 10. And then put 3 B's in there. So 3 of the A's have been converted into B's. What you might find is that if you did the opposite, different experiment, and you put 13 B's in there, 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, and allowed time to pass, you might find that you have 3 B's and 10 A's. Okay, I think I drew that correctly. In other words, you have the same situation here that you have there. If you start with A, eventually you end up with some amount of A and B. If you start with B, you end up with the same amount of A and B as you did in the first case over here. So that tells us that this process is reversible, that there's some sort of equilibrium process going, meaning it doesn't matter what we start off with, we end up with the same situation. So we're going to use what's called a double arrow. That's referred to as the double arrow. And the double arrow is meant to tell us that the forward reaction can occur and the reverse reaction can occur. They can both occur. This is a reversible reaction. Okay? So now let's take it another step. And what I'm going to do here is I'm going to show you a way of thinking about it graphically. We did graphs back in chapter 14 when we were talking about kinetics. We're going to do graphs this way here as well. So now what I'm going to do is, again, let's take A goes to B. But now let's oops, that's not a very good double arrow. Let's assume this is a reversible reaction. And what I'm going to do is I'm going to plot the rate of the reaction. And so this reaction is A goes to B over time. Now, if you remember back in chapter 14, what we said was the rate of a reaction depends on the concentration of the reactant, right? As the reactant concentration decreases, generally, the speed of the reaction slows down. So once you run out of reactants, the reaction stops. So here's what we would expect to happen. As A gets used up, the reaction should slow down. Now, suppose we consider the reverse reaction. Initially, there isn't any B, so the rate of reaction would be very, very small. 0, in fact. But once B starts to build up in concentration, the reaction would increase in rate. So what you would find is that it would get bigger and bigger. The reverse reaction would get faster and faster until essentially they become equal. Okay? So out here, the rate of the forward reaction is equal to the rate of the reverse reaction. And when that's true, when those two rates are equal, we say that the system, this is the terminology we use, is at equilibrium. Okay? It's an equilibrium system. because the rate of the forward reaction is equal to the rate of the reverse reaction. Okay? Now, another thing you could do is you could ask yourself, well, what about concentrations? What would the concentrations of A and B be for this particular situation? And it turns out it depends on the situation, depends on what you're looking at. So I'm going to show you one possibility. So A can turn into B and B can turn into A. It's a reversible process. And we're going to start with A. And now I'm going to plot not rate versus time, but concentration versus time. I'm going to use bracket notation. So concentration of A versus time. And again, we'll assume the simple situation that we're starting with A. What happens? A goes down in concentration, but eventually it'll stabilize. Now what happens to the concentration of B? B is initially 0, but it's going to increase. So I'm just going to say, suppose it does this. Suppose it increases and it comes up like this. Okay, so this is the concentration of B there. Notice how the concentrations, even though they're kind of fluctuating a little bit, they're not really changing out here. These are essentially constant, meaning they're not changing as time goes on. That's another indicator that we're at chemical equilibrium. The system is stable, it's at equilibrium. The concentrations of those two of that one reactant A and the product B, they are not changing anymore. Okay? Now the reason that equilibrium occurs at the molecular level is that when you have a mixture of reactants and products, and both are capable of being converted into the other, what happens is this A might collide with another A and get converted into a B. So it's no longer an A, it's now a B. But this B, excuse me, might collide with this other B and get converted into an A. So both processes are occurring simultaneously. A's are getting converted into B's, and B's are getting converted into A's. And that's what we believe happens at the molecular level. When a system reaches equilibrium out here, meaning the concentrations aren't changing anymore, it's not because it just stopped reacting. It's because the A's are getting converted into B's at the same speed that B's are getting converted into A's. So to us, it appears as though nothing's happening, but at the molecular level, there are things occurring, right? And so it'd be sort of almost like if you took a train and you weighed how much it was. If there were 1,000 people on the train, it would have some weight. Suppose all the 1,000 people that were on there left and a different 1,000 people came on, your weight wouldn't change. It still has the same weight, but that doesn't mean it's the same composition, right? All the people that were originally on the train are off and there's new people on there. They just happen to weigh the same amount. Okay? So that's the idea of chemical equilibrium. The key point of this is this double arrow and the idea that the rate of the forward reaction is equal to the rate of the reverse reaction when we're at equilibrium. That's certainly not the case at the beginning. Here, there's a big change occurring. Here, there's a big change occurring, but later on, will now be at equilibrium. Now, how long does it take for that to occur depends on the specific reaction. It actually depends on the rate constants. If the rate constant is very, very small, that'll take a while to occur, but if it's a large rate constant, it'll happen quickly. So there you go. There's section 15.1, the concept of equilibrium.